a topic that they refer to as motional EMF. Okay, and so when they discuss motional EMF, then what we have is we have a magnetic field. And then in the magnetic field we have some sort of conductive rails. That probably have some sort of resistance. Okay. And then we have a conductive rod that's going to move along the rails. Okay. And so what we're going to have, so I have that the rod is going to move to the right down the rails. Okay. And then what you envision is as it moves along the rails, then we would start off with some initial area, and as it moves, you increase the area enclosed by the loop. Okay. And so, if we have that this dimension is L for the length of the rod as it moves down along the rails, then what we can calculate is that this distance that the rod moved would be our speed times the time, assuming that this speed will be constant, then we can get that distance. And so therefore our change in area is this length times that distance, like so. Okay. And so then, having the rod move down the rails, we increase the enclosed area in the loop. Therefore, there will be a change in magnetic flux. Therefore, there will be an induced EMF, an induced current, and an induced magnetic field. Which way is the induced current? Is it clockwise or counterclockwise? What do y'all think? Have an answer counter, have an answer clockwise. Don't worry, I'll make you vote. I know you were concerned by that.
Yeah, counterclockwise.
Get another counter.
Either way, somebody's going to be right.
You got it. So I'd a little bit prefer a unanimous answer. Well, a unanimous correct answer. Let me be specific. No, unanimous wrong answer is never great. That's like, oh dear, now we got to do more. All right, so who says clockwise? All right, who says counter? All right, so what we get is it's the same stuff, right? Since we increase the area, then we increase the magnetic flux. And therefore, to oppose the change, then my B induced is going to go opposite of the B that created the field to begin with. The B that created the field went into the page, and so therefore my induced B is going to come out of the page. And if it's out of the page, then the induced current will run up the rod around the loop like this, so that's counterclockwise. Is that what we answered? Good. All right, so then what we can do is we can go into Faraday's law. Okay. Okay. And what I probably should do is I did a definite type of thing, so then I can get that my change in area over the change in time is, the length times the speed. And so then you can write this as dA dt once you take your limit. Go from the difference quotient to the derivative kind of things. Okay. And so what we'll find is that since B is constant in this example, then when we go and we take a look at our magnetic flux, B dot dA, then what we'll get is that since B is constant, we can pull that out of the integral. This will give us essentially B dot A, which is the magnitude of B, magnitude of A, times the cosine of the angle between them, XA. And so then when we take our time derivative, BA cosine of theta, and you get this is B times the cosine of theta times dA dt, and that's the quantity we just calculated. And so then when we look at our induced EMF, this is minus, there's only one turn. And then our derivative here would be B times our cosine of theta times our dA dt. And the dA dt is L times V. So this is minus B times L times V times the cosine of theta. Okay. And so this is referred to as the motional EMF. Okay. And to get our theta, then what we'll do is we'll go ahead and pick our area vector. Do you want the area vector either in or out of the page? In. So if we pick that A goes in, like this, then A goes in, B goes in, so then my initial angle is going to be 0 degrees. And so cosine of 0 is just plus 1. And so then our answer is minus BLV. And the minus sign tells us the direction by Lenz's law. Since area goes in, then the positive circulation is clockwise. Now let me do it this way. Since positive is clockwise and our answer was negative, then it goes counterclockwise, which is what we already figured out. So you already figured that one out correctly. Good. Okay. And so there we go. So this is what they refer to as the motional EMF. Okay. And a lot of times they don't worry about the directions or the signs. So what they'll often do is they'll go in and they'll talk about the, absolute value of this, induced EMF is this B times L times V. One thing that we need to kind of note is that B has to be perpendicular to V, which has to be perpendicular to essentially like a length vector type of thing. So they all have to be mutually perpendicular for this result to be the correct result. Okay. It was implicit in the way that we, constructed the solution, is that those have to be in that piece. And then what we can do is we can go in, we can say that the current in the rod is our, induced EMF over the resistance of the circuit. And so you get this is B times L times V over R kind of things. Okay? And then I think that the thing, so this has nice applications. This is essentially a rail gun. So then what they'll do is they'll go in and they'll, ramp the current through the rod in order to project the rod down the rails and launch it. Okay? And so that's always nice. And then the thing that I always like to point out is that we don't actually need the rails. I don't think this is very obvious. Okay, so if we go and we just look at a conductor moving in a magnetic field, so there's our conductive rod, length L, moving in this direction, some velocity, inside a magnetic field. Notice that the L and the V and the B are all mutually perpendicular, like we mentioned before. That was an important bit. And so then what we have is we can go in and take a look that it's a conductor. So inside our conductor, we always have conduction electrons. And so if we look at an electron in the rod, as it moves through the magnetic field, then you have a moving charged particle inside a magnetic field. Therefore, there will be a magnetic force on that charged particle. Okay, and then our magnetic force is Q V cross B. And so then which way is the magnetic force on this electron? And so this would be, right hand rule. This would be number 1, one of the early ones.
Upwards?
Up, everybody agree? Have it down. What's important?
Magnetic field's going into the page, right?
Yes,
Okay.
but it's an electron.
Oh.
Yep. Charge is negative. V, B, force would be up on a positive charge, but since it's an electron, it goes down. And so then what you get is that the magnetic force is down. And what you'll do is you will then gather negative charge at the bottom of the rod, which then means that the top of the rod is now positive. This will establish an electric field, as if that's a parallel plate that runs down through the rod. And then what you get is that you have a charged particle in the electric field. We'll get an electric force. It goes opposite the field. And you continue to build the charge until these forces are equal. You reach equilibrium. So this is Q times E equals QVB times our sine of 90 degrees. The Q's will drop. The sine of 90 is plus 1. And what we get is that E, the electric field magnitude, is V times B. And then the electric field will be equal to the potential difference divided by the plate spacing is the way we usually talked about it. And so then this will be our EMF over the spacing between the positive and the negative is the length of the rod. So the induced EMF is V times L times V, just like we had before. Notice that since the negative particles went down, that's equivalent to positive ones going up. That's the way the current in the rod went in the loop. Up. Now the thing about this is that what we find is that you always induce the EMF. Now whether you have a closed conductive path or not determines whether you get a current and whether that current will create an induced magnetic field. But you always get the voltage. Okay? So the voltage is always present. The EMF is always present. You know. Okay? But only if we have a closed conductive path do we end up getting currents, kind of things. Okay? Faraday's law, the induced EMF is minus N, time derivative of the magnetic flux. And so we can rewrite this as minus N times the time derivative of, BA cosine of theta. And so we can write, if the A and the cosine of theta are constant, then we get the dB dt. And this is equal to our induced EMF. Okay. And one way to write that is that this is equal to some sort of electric field times a length kind of concept. Okay. And so what you get is that in Faraday's law, what we can see is that having a changing magnetic field will induce an electric field. We had to stretch a little bit to get to the E. But this is the general way that Maxwell interpreted Faraday's law. Okay? And so it's worth pointing out, even though we're not really going to do much with that induced electric field concept. Now, the book talks a little bit more about it, but I think it's a little bit beyond where we need to be. But therefore, if you have a changing magnetic field, you'll induce an electric field. So a changing B creates an E. And this is what's the fundamental idea in an electromagnetic wave, is that you have oscillating electric and magnetic fields. So you have a changing magnetic field induces an electric field, and then what you get essentially by Ampere's law is a changing electric field will induce a magnetic field. Okay? And so then they drive one another on to create the electromagnetic wave. So that's kind of the fundamental concept behind Maxwell's equations in terms of why they generate a partial set of partial differential equations, coupled partial differential equations for the electric and the magnetic fields, called a wave equation. Okay, so we're not going to get into that particular piece, but I think it's well worth noting. The other thing that, since I wrote this one down here, that we should probably pick up is that if A and B are constant, then by Faraday's law, we get that our induced EMF is minus N. If I pull the B and the A out,